What's up, folks? It's Glazer here. How you doing? Hope you're having a good week 3 so far. I'm here to talk to you about the lab for Tuesday, which is the type of waves lab. This is not a PhET simulation. This one is basically we're looking at, again, this is a really fun lab that we would have done in class, and it makes me a little sad that we're not doing it. You would have gotten to take slinkies out into the hall and move them up and down and everything. But alas, we have some videos of slinkies moving for you, and we'll talk about that a little bit. So there are two main things. Well, there's a few main things we're trying to show you in this lab. One is the difference between a transverse and a longitudinal wave, okay? And I was looking for a spring all over my house and all over my garage, and I could not find one. My kids apparently do not have a single slinky as a toy. No slinkies?
No, there might be one in their garage.
Okay, there might be one in the garage. I couldn't find it.
Their garage,
okay, I'm recording.
You're recording.
Yeah, but we found a little slinky like this, and I think if I hold it in front of my bald head, you can see the little slinky right there, maybe on the camera. Okay, so basically what we're trying to show you here is two things. There's a transverse wave. Okay, a transverse wave is what most people, I don't know, I would say think of a wave as, right? It goes like that, okay? I don't know if you can see that or not. I don't know where I can, this is all very strange, okay? It's going up and down like that. I'll show you in the video, okay? The particles are going up and down, okay? Looks like a sine wave, okay? The longitudinal wave is also called a compression wave, and that's like if you take the spring and you were to squeeze it together a little bit. Okay, if you have a long slinky, you'll see in the video when you squeeze it together like that, you compress it a little bit, it actually sends that compressed part of the spring through the spring, okay? So those are kind of the two things that the first page of the lab talks about. I'm going to present this so you can see it here. Okay, that's good. I think we're sharing now, maybe? Yes, okay. So this is the lab you're going to do. These are the videos I was talking about up here at the top. Okay, so on the right, the longitudinal wave, that's like if you press it, if you push it, compress it, that thing travels through. Okay, so if you go to the second page, main point of the second page here is look, in the transverse wave on the top, right, the particles are going up and down, but the energy is still going on your screen from left to right. Okay, on the longitudinal wave on the bottom, or the compression wave, even as you compress the spring, okay, now the particles are actually going left, right, and the energy is going from the left to the right as well. Okay, so in a transverse wave, the particles move perpendicular to the direction of the energy. In a longitudinal wave, the particles move in the same direction as the energy. That's a key difference that we're going to keep looking at as we go through this unit. Okay. Okay, and then I'm going to scroll down to the third page. Now, the third page, we're asking you to, this is, sometimes I call this the anatomy of a wave, right? These are the parts of a wave. Again, the one on top, the transverse wave, probably you're more familiar with. Lots of you did this in middle school. The crest is the high part. The trowel, or the trough, I guess is what you say. The trough is the low part. The wavelength is that distance from, could be from anywhere, right, to the same point in that cycle and that oscillation again. But a lot of times we say the crest to the crest, okay? The amplitude is how high the top of that crest is from the equilibrium line of the wave, right, from the middle of the wave, okay? Not from the bottom to the top, from the midpoint of the wave to the top of a crest should be the same as from the midpoint of the wave to the bottom of the trough. Okay, and then if you go down to that second one, the longitudinal wave, this is a little more confusing, okay, but still pretty simple. The compressed part, where it gets squeezed together, is called compression, okay? You can see that. I'm pointing at the screen. You probably can't see that. You can see that where the spring is squeezed together. Rarefaction is the opposite of compression. It's where that spring actually gets pulled apart a little bit. Okay, so the wavelength in a longitudinal wave would be from a point of, for example, compression until the next point of compression. And that's the wavelength there. Okay, all right. And then if we keep going on the next page, now we introduce surface waves. We have some GIF that show you about surface waves here. Okay, a little different here. I'm going to let you look at those and answer those questions. And then the last page, I really like this graphic. I wish I could teach you in person about this. This is earthquakes, okay? There are three main types of waves we talk about with earthquakes. There's an S wave, there's a P wave, and there's a Rayleigh wave, okay? And I want you to look at these graphics for which way the particle motion goes, which way the energy is going. These actually move at different speeds. This is one way we will talk about this, I believe, a little bit next week. This is essentially how we figure out the epicenter of an earthquake, using the difference in speeds between these two waves as they get to different sensor locations around the Earth. Okay, that's what we got. This one's pretty straightforward. On Thursday, we'll hop in. There's a little more about earthquakes tomorrow on Wednesday. On Thursday, hold on one second. Thursday, we'll hop back into the PhET simulations again, and you'll get to kind of play with how to make these different waves and how to change these different things. Okay. If you got any questions, I'll see you in office hours on Wednesday, and hope your week's going well. Bye.